Here's the picture of the life of a computer science researcher who's being really successful and doing things well. Pick a problem that looks very difficult, think very hard about it, discover that it's really very easy, and publish your paper. This is a picture of a less good research plan. Pick a problem that looks really easy, think really hard about it, and discover actually that it's really difficult and it's really hard to publish a coherent paper about it. This is a story about the latter. But there is a reasonably happy ending, as you'll see. So I'm going to show you lots of code. Not all of you will be deeply familiar with Haskell. Please, please, if you get lost in the code, you will get no fun out of this talk. So please stop and ask me. You know, say, what does that underscore mean? I don't mind. You know, low-level syntactic questions, absolutely fine. I'd much rather be speaking in an audience that I was in touch with than one that got lost. So, data type declarations. Are you all right with this? This is a data type declaration declaring maybe of A is either nothing or, that's the vertical bar, just A. And so here's a function, is just, that's meant to take a maybe A and tell you, well, is it just or not? And it works by pattern matching in the way that you all know and love. So the first equation, the pattern matches on just, says true. Function definition by pattern matching, okay? Yes, good, okay. Right, now, if you run this program, well, if you leave out one of the equations here, right, and then you run this program on a just, so I've changed the definition, so I left out one of the equations, then I'll get a runtime error. At runtime, it'll say, no, you called is just, but you didn't provide a pattern for just. Oh, non-exhaustive patterns, yes, that's right. So this is not good, because now your system's in production and it's falling over. Very bad. So what you would prefer is this, right? You'd prefer the compiler to say, your function is just, you wrote it with one equation, it really needs two. Okay? That's our goal. So our overall task then is to provide compile time errors that tell you about missing equations, that's this first yellow block, or perhaps redundant equations. Here's the second yellow block. What's wrong with this? The third equation is redundant, right? It's covered by the first equation. No point in having the third thing. It's cluttering out your code base, it's misleading the people who are reading your code, nothing good about it. Now, you might look at this and you thought, guys, how hard can this be, right? Easy peasy. It's pretty obvious what to do. And that's what I thought. And but it turns out not to be true. So this is GHC's bug tracker. There are around 80 tickets that are attached just to this one issue of these reporting these redundant overlapping patterns, and of which quite a lot are still open. And they're still open not just because nobody got around to it, but because there is something tricky going on. So in this talk, what I want to convince you of is that there is something tricky going on, number one. And secondly, I want to show you of a really nice way that we developed this summer of thinking about the trickiness, okay, and how to sort of tame the trickiness. So, pause. We're going to talk about what's tricky. Number one, interaction between arguments. Here's a famous function devised initially by a guy called Girard Berry, I think, a Frenchman. And so it's got 3 Boolean arguments. And let's see, here they are. There's 3 equations. It's true. What does underscore means match anything? Okay, so quickly, are there any redundant equations? Are there any missing equations? Quick, yes. Beg your pardon? God, my goodness, you are a fast audience. Look at that. Yes. How did you do that? Did you compute all 2 to the cubed possibilities? And check, I don't know, you had some very clever algorithm. But anyway, it's not immediate, it's not obvious in the same way that these are the ones that are not matched, but it is true, right? And in fact, there's something I think you can see here that you might be able to make a linear number of equations with a linear number of parameters that take which all the possibilities have a 2 to the n kind of number of possibilities. So there's something pretty exponential going on here. And in fact, most algorithms to do this, I think all algorithms that I know are worst case exponential. Okay, so that's first little thing. Okay, so far, anything mysterious happened yet? Okay, good. Next one, laziness. Now, I'm guessing that you're a lot of Erlang programmers here, Scala programmers maybe, some of you will be familiar with Haskell, and you'll know that Haskell is a lazy language. And that's wonderful in many respects, but it does have some tricky corners. So I'm going to air my dirty washing with you and show you some of these tricky corners. Now, here, now, if this function was in ML or in another pattern matching call by value language, would the second equation be redundant? It would, right? The first equation handles anything in which the first argument is anything and the second argument is false. The second equation is sort of specialization of that. Okay, now, in Haskell, why is the second equation not redundant?
Because the first one doesn't evaluate the first argument.
The first one does not evaluate the first argument, correct? The first one doesn't evaluate the first argument, it just evaluates the second. So give me a call whose behavior would be different if I deleted the second equation. F what? F and undefined false. Yeah, got two Haskell programmers sitting at the front here. So yes. So in Haskell, error of a string has the type for all A, right? Whenever you've got a Haskell expression, you want to have something of type, I don't know, int arrow int or fugal. You can always say error blah, and it has any type you like. If ever you evaluate it, it'll say, oh, runtime error. So people also often call it bottom, right? So every type is inhabited with this error value. Right, so now f applied to this error value and true. On the first equation, it doesn't match because the second argument was true. On the second equation, it tries to evaluate the first argument to see if it's true, right? To match against this true here. And then it evaluates it and then diverges, or not diverges, but prints exception, irk, okay? If I deleted the second equation, what would happen to this call? It would just return 3, right? Because it would match the third equation. If the second equation wasn't there, f of anything, it still hasn't evaluated the first argument. That's fine, it's a lazy language. So, oddly, the second equation is not redundant. We cannot delete it without changing the meaning of the program, but the function cannot return 2. Isn't that weird? It is not redundant, but the right-hand side is inaccessible. So in fact, GHC these days will print out this slightly mysterious message, right? It doesn't say it's redundant. It just says, by the way, you might like to know that this equation has a right-hand side that cannot be reached. Compiler writers have to worry about this kind of stuff, so that you don't have to. Anyway, okay? So far, so good? Laziness. I'm going to show you more crazy things about laziness. So because Haskell is a lazy language, we'll provide you with ways of controlling laziness, both of which I'm going to show you. So a little sideline. First of all, I have to tell you about empty types. So here's a data type. I gave you a data type earlier for maybe that had two constructors, nothing and just. And you can have data types with one constructor, like pairs. They have one constructor, the pairing constructor. And you can also have data types in Haskell, or GHC's version of Haskell, which have no constructors. Here is one. I say data void. It's as if you said data void equals, and then you gave, well, no constructors at all. Now, this seems rather odd, because what values inhabit void? Only one, right? If you're in Sunday school, and the Sunday school teacher asks you a question, the right answer is always Jesus. In this talk, if I ask you a question, the right answer is usually bottom. So here, the only inhabitant of void is bottom. Okay, so nevertheless, it's a perfectly good data type. You can write functions that consume void. Here, look, this function takes a void and returns a bool. It doesn't do anything to it, returns true. Perfectly fine function. This function G, or I can call, let's see, I can call F. I can even call F. Because remember, I said this guy, who always returns bottom, he can construct a value of type void, right? If you ever evaluate it, it'll diverge or print an exception, but there you go. So this call is fine. And I can even make G2, let's see, what did I do with H? Oh, here's a function H, which returns void. Oh, this is a bit strange. H of x, does it type check? Well, H of x returns a value of type void. Let's look at the right-hand side. Oh, it's a call to H, which returns void. Looks as if it type checks. What happens if I run it? It diverges, right. And that's void is very, that's bottom again. Not an exception bottom, that's a bottom. It's fine too, and then I can call f also on h of 3. And so this time, f will just return true. So it's these uninhabited things. You may say, why would you ever want to? Is this a curious corner? Turns out people do like doing things like this. in real production programs. So take me on trust for that, because I haven't got time to digress into it. But now, have a look at this. So now this is a data type which, in which I've given this bang here is very important. These are strict data constructors. So this is very like maybe. I've called it S maybe. So it has two constructors, S nothing and S just, which evaluates its argument before building the just box. So if you like, the S just constructor is call by value. Is that intuitively okay? So to build an S just value, you evaluate the payload, and then you build the box and return it. Is that okay? All right. So now I'm going to give you the type signature of the function. S may be a void to int. And here's the definition. F of S nothing is 1, and F of S just of blah is 2. Now, question. Is this redundant? Is the second equation, the first equation is fine, right? Is the second equation redundant? Oh, I've got too much focus on the front of the room. So, is the second equation redundant? You think it is redundant because you can never construct an S-just void value, because S-just is strict, right? So an S-just void value would itself be divergent. So I could construct it, right? But what would, if the S-just value diverged, then what would happen when I pattern matched on the first equation? It would diverge then. So the way to say it is this, that the only inhabitants, this is a good way to think about these data types, the only inhabitants of the type S may be void are S nothing, that's an inhabitant, and bottom, not S just the bottom, because S just the bottom, since S just is called by a value, S just the bottom is bottom. So the only two values are S nothing and bottom. And if I give this function S nothing, it'll pattern match on the first equation and return 1. If I give it bottom, it will pattern match on the first equation and diverge. Okay? So yes, the second equation is in fact redundant. You can just delete it. It's not going to make any difference. Now, here's yet another variant. So as well as being able to have strict data constructors, Haskell lets you have strict patterns. So here, this pattern here has a little bang here, and that means I match anything, but I evaluate it first. All right? So if I hit bottom, I'm going to evaluate it. Now, is this redundant? Oh, and by the way, now I'm back to my old ordinary non-strict maybe type, which has inhabitants, the inhabitants of maybe void. Oh, by the way, I've still got a type signature here, right? So that says that the only values that I'm going to feed to this function are, well, nothing or just a void value, but the only void values are bottom. So the only two things I can give it are, well, actually, no, I beg your pardon, I should have added bottom as well. 3 is just bottom. That's also a possible inhabitant of the value maybe void. Should have added that, sorry. Okay, now, if I give just bottom to the second equation, just bottom doesn't match the first equation. If I give it to the second, I'll pattern match on the just, then I'll try to do this bang thing, this evaluate pattern, against bottom and diverge, okay? So the second equation isn't redundant. If I deleted it and put a third equation that matched anything, then I'd fall through to it. But just like that earlier one, the 2, you can't ever get to the 2. It's inaccessible. So it's one of those equations that's not redundant, but the right-hand side is not accessible, okay? All right, so much for bang patterns and laziness, okay? Few other pieces of excitement. This is more syntactic stuff, GADTs. So GADTs is a piece of syntactic, a way of defining a function by a succession of guarded equations that we originally, I think, got from people like Dijkstra, but showed up in Miranda, and I think that's where this is the most immediate. David Turner, the inventor of Miranda, is sitting right here. So I think this is indeed where we got the syntax from. The way you should understand this is sin x, where x is bigger than 0 is equal to LT, where x is equal to 0 is equal to GT, where otherwise is equal to GT, right? So it's just a sort of, there's a Boolean guard and then a right-hand side, another Boolean guard, another right-hand side. Does that make sense syntactically? Understand what that does? Now, so is this exhaustive? Well, you can see that in general it's going to be hard, right? Because you've now got, like maybe this x equals 0, maybe that's covered by x less than 0. We know from arithmetic it isn't. But if there were arbitrary functions, you wouldn't know. So in general, this is going to be rather difficult. But we'd like to solve special cases. Good compilers will do a good job of common cases. For example, otherwise isn't actually a keyword in Haskell. It's simply defined in the libraries, otherwise equals true. So it means exactly the same as writing vertical bar true here. It's just otherwise is more perspicuous. And so it's just an ordinary old definition, but it's helpful for the compiler to know that definition so that it can do a better job of saying this is actually not going to fall through, right? This last case covers them all, okay? So that's the simplest sort of guards, which have Boolean guards. These guards were in Miranda. These pattern guards were not in Miranda. These are sort of Haskell innovation since. So the way you should read it, very much the same thing, vertical bar and some stuff and right-hand side, right? So same, vertical bar, stuff, right-hand side, vertical bar, stuff, right-hand side. Very much the same as we saw here. But this time the stuff itself can do pattern matching. So it says last of x's, where if you call reverse and pattern match on the result, you'll get a cons. Colon is Haskell's infix notation for list constructor. So it says cons of y and something. So it says call reverse, pattern match on the result. If the result is a cons, then you can proceed to the right-hand side. Otherwise, fall through to the next equation. These are called pattern guards. So it's very, very like defining it with an explicit case expression like this, with more explicit pattern matching. But notationally, it's very convenient. Now, you might ask whether this is, are these things exhaustive? Well, the otherwise suggests that it is. But what about this? Maybe here, this is, you probably wouldn't write this, but you could imagine something similar to this. You're calling reverse twice here. And since it gives the same answer both times, and lists are either empty or built with cons, this is actually exhaustive. It's one of those cases. Maybe the compiler should do a good job here. We're never going to do a perfect job, but maybe we should do a good job. Okay, so let's see, and you can mix the two, which I shall skip, and view patterns I'm going to skip. Let me say one, so that's to do with, what have we talked about? Laziness and some syntactic baggage from pattern matching, pattern guards and so forth. Now we're going to talk about another thing, which is long distance information. I'm just trying to motivate why overlapping patterns might be a bit hard to do. Have a look at this. Here's a data type with 3 constructors, A, B, and C, the grade for your exam. And for some reason, the programmers defined it with a pattern match on A at the top here, and then a kind of fall-through pattern, which matches all the other grades, G here. And then in the right-hand side is pattern matching on G. Do you understand what this program is doing? Right? Is there any confusion about the semantics of what this is doing? So, there's not a one Haskell programmer. So should I report? Usually if I saw a case expression like this one, I'd say, oh my goodness, look, G, it's of type grade. Grade has constructors A, B, and C. There's only B and C here. Missing pattern. Would you like that as a programmer? Would you like GADT to say missing pattern? No! You would say, stupid compiler, look, I matched A up here. Don't forget that. Keep in mind all the pattern matching that's been done somewhere outer or above, and sort of bubble that down to the particular case expression you're now looking at. And again, you may say, you shouldn't write your program like this. You should do all the pattern matching in one place. But believe me, programmers, when they get into production, they do stuff like this, and they start complaining like mad if the compiler doesn't do a good job. And I have a lot of sympathy with that. There are reasons you might want to do something in a particular way. It's not the business of compiler writers to tell you how to do it. Okay? So this sort of long-distance information is important. So here we are, a problem that started looking simple, and now it's sort of getting a bit more complicated. And we haven't even talked about GADTs, right? Double the fun. Look, here is some, so GADT, generalized algebraic data type. So who's come across GADTs in some shape or form in some language? Probably a little more than half, fine. So I'm going to just mostly assume that you know what I'm talking about here. This is a data type, except it's declared with a slightly different syntax in which I give the type signature of each constructor. So it's got 2 constructors, tint and tbool, just as maybe had 2 constructors, just and nothing. This one has tint and tbool, and here tint has the type int to t of int, D bool has type T to T of bool. So there's these constructors have return types that are not just TA. That's what makes them GADTs. Now, if I tell you that getInt has a type signature, it has type tint to something, well, now I can match against tint I. Are there any missing equations now? Would it, what about T bool? Shouldn't I say T bool of B? No, 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 because? Because what? Because the type signature of T bool says, how could I match against the T bool? How could I possibly give a T bool argument to this function? It only takes a tint. The caller's going to make sure that he only gets past the tint. And as it happens, there's only one way to build a tint, and that is with this tint data constructor. T bool can't occur here. So yes, this is, fine. This is an exhaustive equation. And the long distance information applies here as well, but in a more interesting way. Look at this. Here's through here has two arguments. The type signature says they're both of type TA, look. Right? I match on one of them, the first one, and then in the second one, in some nested place, I match on Y. Ooh. Last time, I was matching on the same thing that I matched. Now I'm matching on some completely different thing. And yet the fact that inside the tint branch, I know that A must be int. So inside this first equation, I know that A equals int. And since A is equal to int, Y now has type tint, right? So this case is exhaustive, and similarly for the second one. Have the idea? So now the long distance has become even more long distance because it's going through separate parameters and through the type system. Are we having fun? Yes. Good. Okay. So how are we doing? Yes. So we're going to move to video speed. I'm going to skip this one because it'll be. It's just more of the same, only more so. So I hope you get the idea for GADTs. They definitely make the pattern matching overlap problem much more, let's say, interesting. Now then, I haven't finished. We've got pattern synonyms, which I'm not going to tell you about. There's fairly recent innovation in Haskell, but that allow you to abstract over patterns and make this problem a bit harder. So in the end, this is the payload of this first part of the talk, right? You've got all of these features, right, of the language that interact with each other in somewhat complicated ways to make the simple task of saying which equations are redundant quite hard to achieve. Okay. So now I hope you're feeling in that state that I've led you into the pit of despair. Now you think, I'm glad I'm not the person who has to write that compiler. And now I'm going to take you by the hand and lead you back into the heaven of insight. So let's see. Oh, what happened? Oh, I went backwards instead of forwards. So at this stage, I met George Karakalis and Tom Shrivers. Well, I knew Tom Shrivers from somewhere. George was Tom's PhD student. He came to Cambridge for a week and did quite a lot of work and figured out really quite a nice approach to bringing order to all of this. And we wrote a paper that was published 4 years ago at ICFP called GADTs Meet Their Match that was about this exact problem. And it had this magnificent figure, which I was terribly proud of, that said essentially all you need to know about how to compile pattern matching. But it's not a small figure. This is the whole thing. But nevertheless, I look at this and it gives me a bit of a headache. And we tried to implement it. Indeed, GHC's current implementation really does have more or less this. But it didn't work very well. It was quite slow. And it was quite hard to understand. So essentially, it was still somehow too complicated. And it didn't do everything. It didn't deal with pattern synonyms, for example. It was a big step forward, though. So then, what are we going to do? When things like this happen, you just have to think hard. So this summer, Sebastian Graf, who is a PhD student at the University of Karlsruhe, he came to spend a summer at Microsoft, and he's a very clever fellow. So we did a lot of thinking cap stuff, and I'm going to show you what we did. So here is the simple idea. We're going to split the pattern matching overlap and redundant equation problem into two parts. Part one, we're going to sort of somehow desugar all these complicated pattern matching wimwams into a simple form that I'll just call GADTs. Right? So I'm going to take many complicated things and turn them into one simple thing. And then I'm going to take the one simple thing and turn the GADTs into what I'll call a fact base, which is a kind of collection of constraints to tell you about. So at the moment, the only takeaway from this slide is we're going to do 2 bits, right? So step 1, let's desugar pattern matching into something simpler. So here is an equation. Please don't be intimidated by this yet. I'm just in yellow, I've written the original function, and in blue, I've written its desugaring into this sort of simpler language. The simpler language is actually a kind of subset of Haskell, actually. So what have I done here? So here, what have I done? There's a bit of excitement going on here. Here's a pattern. It's got a nested pattern. There's a nested pair. There's a bang pattern. There's an as pattern. I haven't mentioned as pattern. That just means that wise is a name for the whole thing, but I still want a pattern match on it. And there's a guard here. And then I've got to fall through to this one. So it's a moderately sophisticated pattern match. So how do I desugar it into guards? Well, imagine that I had f with just 2 parameters, a's and y's. Those are the names of its parameters. And the first thing I do is I match the first parameter against just, right? So this says, take a's and match it against just, binding, and if it succeeds, then we're going to carry on down this sequence of guards. If it fails, we'll fall through to the next equation. But let's suppose it succeeds, and a's is indeed a just, and I'll call its payload t. Now what happens? Oh, up here, the payload would better be a pair. Very good. Match t against the pair, and let me name the components of the pair, x's and v. Okay, now what? Now I've got to be strict. Okay, so now I'm going to have a funny kind of guard that just says bang x's, meaning evaluate x's, and assuming that doesn't diverge, carry on, but if it diverges, then diverge. Okay, what's next? Now I've finished here, there's nothing more to do here. Then what about the second argument? Well, the second argument was called y's, that's fine. So now I've got to match y's against y cons w, that's this match here. Match y's against y cons w. I'm just giving arbitrary names to these otherwise anonymous pieces of pattern. And what about w? Well, let's see. W is not going to be used at all. But I do need to check that, what's this, y is bigger than 3? Oh, so let me just name the expression y is bigger than 3 with a let. I'll call it b. And now I'll match b against true. Okay, so I've got I've got a new kind of thing here, this let thing, that just gives me a name for a computed value, in this case b bigger than 3, y bigger than 3, and then I'll match b against true. And then if all of those long sequence of guards succeed, then the result is RHS1. And by the way, y and y's and x's are all in scope. They've all been bound in this sequence. So far, so good? Nothing really hard here. All I've done is I've sort of operationalized this nested pattern match into a sort of single linear sequence. Okay? And I can do this for all the, Haskell has a lot of syntactic forms for patterns. They can all be turned into this form. Now then, what about the second equation? If any of those fail, fall through to the second equation. In the second equation, I match a's against nothing. And now what's this doing? Oh, this is because, remember at the top here, this is a single name for the first parameter is a's, the second parameter is y's. But in this right-hand side, I just happened to have called the second parameter z's. Fine, no problem. I'll just make a binding for let z's equals y's because it's in scope, because z's might be mentioned in RHS2. Okay? Easy, really. So this is a kind of simple and uniform process. It's I've already said all this. It's enough to express all of these, various syntactic forms that occur in Haskell, all into 3 forms of guards. Look, here they are, quite simple ones, right? A bang pattern, a bang guard, a matching guard with a variable here, and a let. Okay, nothing up my sleeve? All right, that was quite simple. So I factored the problem into lots of complexity of pattern matching, all slapped into this one thing. Now, so far so good? Yeah?
Why the let? Why not just have a pattern that is variable?
Oh, why did I have a let? I could, instead of saying let b equal y, I could have said b left arrow. That's right. So, but then, remember that here, in my syntax, I'd have had to say kx1 is a bound for y. Remember, this is very specific. This is not this k here. This is k applied, a constructor applied to variables, right? It's not an arbitrary pattern there. It's always a constructor applied to variables. Now, let, if you like, is a variable on the matched against an expression. So you could almost say, if I just wrote it x left arrow e, it would have been the same thing, right? Oh, and the other thing here is I've made it simpler by y here. That's always a variable. If I need an expression here, then I'll let bind y first. Okay, so I've sort of factored it into 2. But remember, this is not arbitrary patterns. The only pattern you get in the second thing is constructor applied to variables. It's all flat, if you like. Okay, anybody else? I may refuse to go on at some point unless you ask some questions. Yeah, Dominic.
Does the lazy patterns have some special syntax as well?
Do lazy patterns? Oh, twiddle patterns. Yeah. Yes, so Haskell already also has a twiddle form for patterns. So no, they don't. They just turned into a let binding and some sort of nested pattern matching off to the side. So no, they don't need anything else for them. I can show you. Yes?
Any patterns you've covered already that aren't covered by this?
No, are there any patterns I've covered already that are not covered by this? No, everything I've shown you is covered by this, yeah. So it's kind of, provided we do have to allow pattern synonyms. These Ks can range over pattern synonyms, though we do have to do some work for them, for what it's worth, but yeah.
So I think my head says they exploded stage still. But is this, you're essentially taking the expressions and transforming into something like a single static assignment?
It kind of has something of the same, the question is this like doing SSA, single static assignment form? It has something of the same flavor. I'm flattening everything out. I'm nailing every intermediate sub-pattern and putting it in a much more sequential way. It has the same flavor, yes. You would almost think of it like SSA for pattern matching. Yes, thank you. It's a good analogy, actually. Yeah. Yeah.
How's the performance of this compared to the 21st century?
How's the performance of it? Oh, remember, this is just for doing pattern match overlap checking. I'm not going to run this. Oh, you mean, does pattern match overlap checking take too long? Well, this part is not the part that takes long. This part is linear in the size of the equations and so forth. There is a bit that can go exponential on you, and we have to have a sort of throttling mechanism that says, I mean, there's a fundamental reason why it goes exponential. We saw it in that Berry example. And so there's a throttling mechanism that says, oh, users hate it if their compiler just says. So we sort of give up and say, I couldn't really tell you about this pattern match check. That's better. Okay, thank you. Anybody else? Yeah.
So do you actually warn if you throttle?
Oh, if you get into that situation, I think we may not actually say I ran out of fuel. We may just give you sort of slightly bogus messages. I'm not quite sure. We'll wait until somebody complains and says, you ran out of fuel and you misled me, or you failed to report something. But reporting that you run out of fuel is not very helpful to programmers, right? They think, I don't know what to do. It could be, give me more fuel. But if it's exponential, then the lifetime of the universe will not be long enough. Okay, so how are we doing? We're finishing at the 15:15? Yes, okay, 10 minutes, good. So second step, how are we going to find those missing equations? So here's how to think of it. Think of each of these things now, each of these equations. I've turned my equation into a single f, a, b, c, all variables, and then each clause with the right-hand side has a sequence of guards. That's my initial step. So I'll call each of these here clauses. So now my task is to say, I want to find out which things are not matched by any clause. So imagine here that I feed in all values at the top, and then I feed it through clause 1s. Well, it will match some, but some will fall through. So then there's values not covered by clause 1, feed them into clause 2, values not covered by that, and you feed them all the way to the bottom, and if anything pops out at the bottom here, any values not covered by any clause, those are the guys you want to report, okay? Now, how can I do this in a compiler? I need a way to represent a set of values. How can I represent all values, right? I can't represent by something infinite. That makes compilers take a long time. So I want a way to represent sets of values inside a compiler. A good way to represent it is by something that looks very much like a refinement type. Look, so I'll call it delta, one of these fact-based things, and it's going to take the form of curly braces and then variable of a particular type, vertical bar, constraints. So x colon maybe bool with no constraints represents all values x of type maybe bool. So bottom, nothing, just bottom, just true, just false. Those are the values of that type. Now, the second one here, x colon maybe bool such that x matches nothing. That's That's a much smaller set. So the bit after the vertical bar is the constraints. Those are very guard-like things. Those are the constraints, things that must be true of these values. So here, you can see that's just the set nothing. What about x may be bool where x is the form just y for some y, just y of type bool? Well, those are all the just things. X couldn't be bottom in that case. X could be just bottom, it could be just true, it could be just false. So this is a reasonably compact way of representing sets of values. And that's what I'm going to do in practice. And indeed, there's a whole research stream called refinement types, in which the types in your programming language look very like this, right? And so this is just picking up on well-known technology. Now, let me show you an example. Here's an equation, f of just true equals some right-hand side, desugared into this guard language. I have to flatten it out, so I'll first match on x to get just y, then match on y to get true. So I just flatten the patching into the sort of SSA type form. And now imagine feeding through. We start off with a set of all values of type maybe bool, because my equation said, my equation had type maybe bool. Now I'm going to feed in the set of all values, that is this. So you should think of this, this delta thing as really a data structure that the compiler manipulates. It's a representation of a set of values. And so we start off with x of type maybe bool, and then somehow we feed it through this equation to get the values that are not covered by the equation. What values are not covered by the equation? Well, there are two ways in which we could not cover. We could fail on this first guard, so maybe x is not just. So look at, so here, that's the x's where x is not just. Oh, and by the way, it's also not bottom because we have matched against that just. So that's the first possibility. But the second possibility is we matched against x and succeeded, right? So this guy succeeded, and then we failed against y. So there, x did succeed in matching against just y, but y turned out not to be true and not to be bottom. That's the description of the values that do not match any of these equations, right? The ones that fall out of the bottom of this equation, okay? And the nice thing is that, remember that big figure? This is the main payload of the talk, if you like. This is a description of what values are not matched by an equation. So I'm just going to go through this and then I'll wrap up. So look, so U stands for uncovered, takes a delta, that is a fact base, that's right, that's representing a set of values, and G's, which is a list of guards, right? So G's is one of these chaps here, you know, just Y, oh dear, I'm not very, they're here, this lot, these are the list of guards. Now, oops, right, so now, and the U is meant to return the subset of delta, the incoming delta, whose values do not match the guard's G's. If the set of guards is empty, oh, darn, I forgot to fix this typo. If the set of guards is empty, the result is delta, right? The set of values that do not match the, oh, did I get this wrong? No, the set of guards, the values that do not match the empty guards. No, it is right. Set of values that do not match the empty guards. There are no values that do not match the empty guards. We succeed, right? So nothing falls through. So, sorry, empty guards, empty here. Now, what about this pattern? So I'm just now proceeding by recursion, just doing pattern matching equation over the type of list of guards, right? I'm writing the compiler. Guards can take these three forms. Well, let's try the three forms. Maybe the first guard is k y's matches x. Well, there are two possibilities. The ones that do not match this guard either look like delta extended with knowledge, that's plus, with x not equal k and x not equal bottom, that is because x is not a k thing, nor is it bottom, or the other possibility is that we do succeed in matching the k, but fail somewhere in G's. In that case, so union, the set of values gotten by looking at G's in a fact base in which I know that x does match ky's. It's so simple. The two possibilities are I match k or I don't match k, and then I just recurse. And that's the only hard equation. This next one is quite easy. If I am looking at a strict pattern, then, well, I've just got to say it never falls through directly, it never fails directly. I can just carry on with G's, the guard's G's, knowing that x is not bottom. And finally, for a let, I just carry on with G's adding a let binding so I extend delta with a let binding. So I need to have a way of extending this fact-based delta with extra facts. So I should think of the fact base, this delta thing, as accumulating facts that I know about my values, and in the end, I've got to cough up a missing value. And that's really it. So now the only remaining thing to do in 2 minutes is to, so I'm going to video through this. Our last task is to report what values have fallen through. So given a delta, how can I cough up a value that, so given this delta, say, the ones that fall through here, how can I produce, what you want to show to a programmer is, here is a value that is not matched by any of your equations. You don't want to just say the equations aren't exhaustive. You want to say the equations aren't exhaustive, and here is a counterexample, right? And it turns out to be not very hard to systematically take a fact base like this and cough up a value that doesn't match. And I'm not going to go through that. So the last thing to say is, does this scale up to all of Haskell? Yes, with all its glories, and I'm not going to, also, it's not just uncovered equations, it's redundant and inaccessible equations. We also need to talk about pattern synonyms. We also need to think about GADTs and type equalities, and why has my computer suddenly gone blank? Oh, long distance information turns out to be really easy because as we pattern match through here, we extend our fact base, and then we can just transport the fact base through hyperspace to be the starting position for G here. That's really easy. So this is really the final slide I wanted to say is that having got, this was sort of where we were in the summer, we've sort of gone from happiness to despair, but back to happiness. So what I really want you to mainly take away is the idea that that by taking this very simple set of guards and separating the desugaring part from the reasoning about constraints part, we're able to factor the problem into two in a way that makes each part is dealt with separately and it become much more simple and modular in that way. And indeed, GHC's implementation, as of today, more or less implements this new plan, thanks to Sebastian. Very good. Thank you very much. Let's have any more questions.
Right, if there is one question, I can take it.
Yeah, so somebody hasn't asked a question yet. Yes, thank you.
So when you have this desugared guards and you find a problem with one of them, how do you get that back to an error message in a kind of the sugared form for the user?
Yes, right. So once you've desugared everything, you're pointing out that a disadvantage of desugaring is that you might report errors about something that's very different to what the programmer wrote.
Yeah.
But here, it's not so hard, actually, because we never need to think about the desugared thing. Think about a function like this one. Here. So even though I might have desugared this pattern, what I want to report is these equations are not exhaustive. Here is a pattern that will not, here is a value that will not match any of them, right? So I just want to report f of just false will not be matched, for example, right? And it turns out not to be hard. It's not hard to produce. So you don't have to produce anything in pattern syntax, right? The original syntax the programmer wrote. You just have to say, here is a value, written in nested form, of course, that will not match. And it turns out that turns out not to be hard. So it's a good general question, but in this case, it's not a problem.
All right, that's all we have time for. There's a coffee break coming up now. Talks resume at 15:35.
Good. Okay, thank you.